All right, so I'm going to go ahead and get going. If you have any questions, please just type them in the chat window and then I'll see them. What I'm going to do is go through and give you a review. I presume you've already studied for test one, obviously, so you have some idea of what I'm talking about. It's going to be kind of a quick run through. Like I said, I am assuming you remember at least something from earlier in the course and the chapters. If there's something you don't remember, though, or something you would like me to clarify, don't hesitate to ask in the chat. You know, this is for you, not me. So anything I can do to explain something that's confusing you, just type it in, and then when I see that, I'll answer that as we go. All right. I'm going to use the whiteboard for most of this. So first thing, we're going to talk about potentials. A potential, you have to remember, is just a separation of charge over space. Right. There are many different kinds of potentials. A battery is an example of a potential where the positive and negative charges are separated by the room in the battery. All right, so potential is a general term. Okay. In this class, mostly what we're talking about are membrane potentials. So these are simply the separation of charge across the cell membrane. That's all a membrane potential is. Now, within membrane potential, there are lots of different subtypes. We'll talk about a resting potential. Okay, I'm just writing resting potential, but really it's resting membrane potential. This is basically the membrane potential when nothing's going on. Right, we'll talk about the action potential. Right, and this is a signal. This is the electrical signal that neurons use. We'll also maybe talk about EPSPs and IPSPs. More likely, we'll talk about those next time. EPSP stands for excitatory postsynaptic potential. Okay, and IPSP is just inhibitory postsynaptic potential. All right, but all of these are examples of membrane potentials, which is an example of a potential. The term, the abbreviation for this is V sub M. Okay, so potentials are measured in volts. In neuroscience, we actually measure in millivolts because they're very small. But this is a term, V sub M, that we use for that. All right, so I have to get used to this new whiteboard, sorry. All right. When we look at any cell, we have the cell membrane. Okay, the cell membrane keeps the outside out and the inside in. Now, with the cell membrane, if you remember, it's semi-permeable. Okay. Permeable means things can go through it. Semi means some things can go through it. Okay, so semi-permeable membranes, some things can pass through, but a lot of things don't. Okay, so some things that go through, things that are fat soluble, things like heroin, things like carbon dioxide and oxygen gases can just pass right through. Other things cannot. Okay, so things that can't pass, large proteins, most neurotransmitters, things like that can't pass through that membrane. In addition, ions can't pass through. So obviously when we're talking about potentials, we're going to be talking about sodium ion, potassium ion, chloride ion. In terms of the resting membrane potential and the action potential, these are what are important. Other ions that do come in, as you know, calcium is an important ion for some things like learning and memory. Okay, so ions can't pass right through the membrane. We can control the flow of ions and the concentration of ions through pumps and ion channels. Okay, so pumps use energy and go against the concentration gradient. Ion channels are just tunnels through the membrane that allow things to go. Now, when the neuron is at rest, okay, so nothing special is going on, we are going to have a higher concentration of sodium in the outside, in the extracellular fluid. We'll also have a higher concentration of chloride ion outside the cell. There's still sodium and there's still chloride inside the cell, but a much, much lower concentration. Inside the cell, we'll have lots of potassium. Okay, so we'll have high potassium, low sodium, and low chloride ion. Now, the concentration of these ions are tightly regulated. You have heard over and over about people who have problems with their electrolytes, right? When your electrolytes get out of balance, your body doesn't work real well. One of the things that really doesn't work well are your neurons. Okay, so physiology is going to maintain the concentration of sodium, chloride, and also potassium in the extracellular fluid. Now, if you think about a cell, okay, a cell can't really control what's going on in the world around it. All it can do is control itself, what's inside itself. You can kind of think about like you trying to control the temperature of your room. You can control the temperature of your room a lot more easily than you can control the temperature outside. Okay, so in the extracellular fluid, we'll have low potassium, high sodium, high chloride. So what the cell does is going to use a series of channels and the sodium potassium ATPase pump to create this environment. Okay, so the cell works to increase potassium and get rid of sodium and get rid of chloride. You know, we're not going to worry too much about the details. That's beyond the scope of the course. Obviously, the sodium potassium ATPase pump is important for these. There are ways to regulate chloride, but again, we're not going to worry about that in this class. All right, just know that the cell can control its internal environment, and what it does is pumps in potassium, pumps out sodium, and also chloride. Okay, so when we're at rest, we have a whole bunch of proteins inside the cell. things like DNA, ribosomes, enzymes, microtubules, all those things that make up the structure of the cell. Okay? Collectively, those are known as organic anions. Okay, so basically proteins are slightly negative charged. So when we look at all of those things on the inside, we look at the difference in concentration in potassium, sodium chloride, all of that stuff. What we end up with is a slight excess of negative charges inside the cell. Okay. Again, you don't need to worry about the details. If you go on to advanced neuroscience, there are equations where, based on the concentration of the ions, based on the permeability, you can calculate exactly what the resting membrane potential should be. Right. But we're just going to chalk it up to magic and know that we have a slight excess of negative charges inside the cell. Okay, so at rest, our V sub M equals slightly negative. And I did say the number I want you to learn is minus 70 millivolts. Okay, so what that means is the inside has slightly more negative charges. You can also flip that around and say that the outside has slightly more positive charges. Okay, so that's at rest. It turns out I do want you to know the sodium, potassium, ATPase pump. Just make sure you look briefly at that. You don't need to know too much detail. Don't overthink it. Just know that this helps keep potassium high and sodium low inside the cell. If the sodium potassium ATPase pump doesn't work, it's going to change the concentrations. So instead of having a very high concentration of potassium inside, we'll have less high concentration inside. Right? And that does have some implications for the membrane potential. Any questions on the resting membrane potential? All right, so let's say here's outside. Here's inside. Remember, the potential is the separation of charge. All right, it's the difference. So if we schematically draw this, the outside will be a little bit positive compared to the inside. Okay, and the difference, the size of the difference, the size of the separation of charge will be 70 millivolts. Now we always go inside compared to outside. So inside we have an excess of negative charges. Okay, so it's minus 70 millivolts. What would happen if I added some sodium to the outside? I want you to think for a second. What would happen if I increase the concentration of sodium? In that case, what I'm doing is I'm adding more positive charges, right? So I'm making the outside more positive. The flip side of that coin is when I do that, I'm making the inside more negative. Okay, so this minus 70 millivolt will get more negative. So maybe it goes to minus 75 millivolts. Okay, so movement in that direction, increasing the separation of charge, is called a hyperpolarization. Now on the exam, I will ask you, what happens if we change the concentrations of the ions? So you need to understand the role that they play and how to predict how the membrane potential would change. Okay, so here I added a bunch of sodium ions. I made the outside more positive. What would happen if instead of doing that, I added some positive charges to the inside? Now the difference between the inside and outside is less, right? So in comparison, I have a smaller excess of positive charges outside. So if I were to add sodium to the inside, this number, instead of going to minus 75, the difference is smaller. So instead of minus 70, we'd be at minus 65. That's called a depolarization. One way to think about it is think about it in terms of a difference in test scores, okay? So let's say the outside is one student, the inside's another student. Let's say the outside scores 90. Let's say the inside scores 20 points. Okay, here we have lots of positive points, right? Here we have fewer positive points. All right, what's the difference? Well, here the difference is 70. How's the inside? Well, the inside did worse, right? The inside did not study very much. So the inside is minus 70 compared to the outside. Now, what if I add some positive charges? I add some points to the outside. So now instead of 90, let's say we're 95. Now what's the difference between? It's gotten larger, right? Because we added points here. So now instead of minus 70, will be minus 75 millivolts. We've increased the difference. Likewise, if instead of doing that, we'll go back to 90 and 20. In this case, if I add some points to the inside, I add some positive charges. So instead of 20, now let's say we're at 30. Now the inside is still more negative, right? But the difference is smaller. So instead of minus 70 where we started, now we'll go to minus 60. Okay, so that's what would happen if we had positive charges to the outside, positive charges to the inside. Make sure you could also predict what would happen if we added negative charges. Okay, so let's say we're here, we're at minus 70 millivolts. Let's say I add some chloride ions to the outside. I increase the concentration of chloride ions. That's making the outside less positive. It's like taking away points, right? So when we do that, the difference between the inside and outside gets smaller. Okay, so we, instead of minus 70, we would go to something like minus 60 millivolts. And you'll see some questions like that on the exam. So if this doesn't make sense, let me know and we can talk about it. Now with the action potential, this is how the neuron knows something's going on. The action potential carries information. So if you think about a sensory neuron, here you got your foot. And then here you have your sensory neuron near the spinal cord. Okay, that's where the cell body is, and that's going to send information into the dorsal root of the spinal cord. If you step on a nail, that's going to stimulate this. Somehow that message has to get from the sensory receptors up to your spinal cord. Okay? And that's going to be done through electrical communication, in this case, the action potentials. So when we look at the action potential in a typical multipolar neuron, we have the axon hillock. That's where the axon and the cell body meet. Some people call this the trigger zone. Okay, because this is where the action potential begins. Okay, the cell body doesn't have action potentials. Okay, the action potential is specific to the axon. The terminals don't have an action potential. Okay, the action potential goes only along the axon. All right. I'm going to draw this a couple ways. This is a review, so hopefully you can put these together. Here we have a trace. Sorry, I'm trying to draw this on a drawing pad, and I'm not great at it. That's why these aren't particularly neat. All right, so here I have my cell membrane. Here we have time. Here we are at rest. Remember, we start at minus 70 millivolts. Now you know, because you've read psychopharmacology and understand how neurotransmitters work. At rest, what might happen is we'll get a little depolarization. Okay, and this is going to be an EPSP through neurotransmitter acting. It could also be through a sensory receptor. All right, we're going to get a little depolarization until we reach minus 55 millivolts. And 55 millivolts is threshold. And this is threshold to generate an action potential. Okay, so we get this excitation. Now we get this massive depolarization. The exact number doesn't matter, plus 20, plus 30, somewhere in there. You get a massive depolarization. Shortly after, we get a repolarization. We go a little bit past minus 70 to about minus 75. And then slowly return to rest. Okay, so this phase is called the depolarization phase. This phase, until we hit back to resting membrane potential, is the repolarization phase. Okay, so my neuron's sitting here, nothing's going on. Something stimulates the neuron. The membrane potential at the axon hillock reaches threshold. That triggers an action potential, which then travels down the axon and carries information. Okay, so right now we're looking at the beginning of the action potential at the axon hillock. Now we need to tie this to events. Okay, so I'm gonna list the events. First thing, we hit threshold. Okay, once we hit threshold, voltage gated, sodium channels open. Okay, when those channels open, sodium rushes into the cell. Okay, so here's my cell membrane. Here's my voltage gated sodium channel. I got a whole bunch of sodium. outside. I have a little bit, but not nearly as much inside. When we hit threshold, it changes the shape of this. So this now opens up. I can't draw it real well here, sorry. So when this opens up, these sodium ions flow down their concentration gradient into the cell. And so now I got a whole bunch of positive charges flowing into the cell. That's going to depolarize my cell. Okay, so here where my voltage gated sodium channels open up, sodium's going to flow into the cell. Now, how long will sodium flow into the cell? It'll flow in until it reaches equilibrium, meaning the concentration inside and outside are equal, or until those channels close. Okay. Now, when the sodium rushes into the cell, that's going to give me a depolarization. Somewhere in here, before the peak, okay, somewhere before the peak, voltage gated potassium channels open. Now, when these channels open, remember I have more potassium inside than outside. So potassium will flow out. Okay, so when potassium flows out, if I just have potassium flowing out, that should make my cell more negative, right? It should hyperpolarize my cell. But if you look at the trace, that's not what happens. Remember, the potassium channels are open here, but we still get a depolarization. Okay, the reason for that is during that time, both sodium and potassium are flowing at the same time. But the flow of sodium is so much greater than the flow of potassium that sodium wins. Okay, so potassium flows out. At the peak, the voltage gated sodium channels close. Okay, now when they close, they become refractory. And what that means is they can't respond. They can't open again for a short time. So they can't open again for a few milliseconds. All right, so here we have voltage gated sodium channels open. Sodium flows into the cell, causing this depolarization. Voltage gated potassium channels then open up and potassium starts to flow out. All right, but sodium's coming in so fast, it doesn't matter. We continue to get this depolarization. At the peak here, the voltage gated sodium channels close. Okay, now if you think about this, right, here we are. What caused the voltage gated sodium channels to open in the first place? Well, we hit threshold, right? So if you're above threshold, those sodium channels want to open up. At the peak, are we above threshold? Yeah, we are. So those channels should open back up, right? That's why the refractory period is so important. Okay, the channels close and can't open again until we reset. Okay, they're on a timer, so they're refractory for a couple milliseconds, which is enough time for us to return to rest. Okay. Again, we're above threshold here, right? They should open. but because they're refractory, they don't. All right. Now, when they close and become refractory, now potassium flows out unopposed. Okay, so as the potassium flows out now, as it's going to decrease the number of positive charges inside, right? It's going to make us more and more negative. Down here at this point, the voltage gated potassium channels close. Okay. Now, I told you that the overshoot a little bit. So instead of stopping at -70, there's a little bit too much potassium flows out, and we're at -75. Over time, the excess potassium that flowed out diffuses away and has no impact on the membrane potential. Okay, so what I'm going to do is kind of walk you through it here on a fresh thing. You should be able to follow along. Okay, so as I'm going through it, you go through it in your head. I'm trying to help you study here a little bit. By the way, the time for the entire thing is 1 to 2 milliseconds. That's how long an action potential lasts. All right, so here we are, -70 millivolts is our resting membrane potential. -55 or so is threshold. All right, so here we are hanging out. Everything's cool. Suddenly some neurotransmitters released, and I get an EPSP. That EPSP is going to depolarize my membrane potential. If we hit threshold, first, voltage gated sodium channels open. Those open channels allow sodium to flow in really fast. So I get a massive depolarization. Here, the voltage gated potassium channels open up. So potassium's flowing out, but we know sodium wins. Okay, so we keep getting our depolarization. Now my sodium channels close and become refractory. So that potassium can continue to flow out unopposed. And I get my repolarization. My voltage gated potassium channels close, but a little bit too late. We're at -75 or so instead of -70. Now those excess potassium ions flow away and I return to rest. Okay, so that's essentially the action potential. Now it's going to start at the axon hillock and then it'll move down the axon. Now, what causes the action potential? There's a couple levels to answer that. What I'm looking at, what causes this depolarization is the opening of voltage gated sodium channels. Okay, so we need these and the voltage gated potassium channels to have an action potential. Okay. So based on that, here's my cell, here's my axon, here's my terminal. Based on what I told you, where are there voltage gated sodium channels? Is there an action potential in the cell body, the soma? I told you no. How come? Because there's no voltage gated sodium channels. The action potential goes along the axon. So do you think there's voltage gated sodium channels there? Yes, obviously. There are no action potentials in the terminal. So does the terminal have voltage gated sodium channels? No. Okay, so it's important for you to remember where the channels are. Okay, if we magically put voltage gated sodium channels on the cell body, guess what? We'd have action potentials in the cell body, right? But your body, the cell, is set up so that the mechanisms to take proteins to the right place, right, only take the voltage gated sodium channels along the axon. All right, so now let me ask you a couple questions. Here is, let's say, your typical action potential. All right, there's a drug, a toxin, tetrodotoxin. Whoops. You probably heard of tetrodotoxin. This is in fugu, pufferfish. All right, what this does is blocks the voltage gated sodium channel. So on an exam, on the final exam, I will give you different toxins. I'll tell you what they do, and you need to be able to predict how they would affect the action potential. All right, so tetrodotoxin, the book talks about, I talked about in my lectures, but let's work it out here. How would that affect this? What I recommend you do is think it through. All right, so this is going to block voltage gated sodium channels. Will tetrodotoxin have any effect on the resting membrane potential? If we're at minus 70 millivolts and I give the animal tetrodotoxin, will that change resting membrane potential? Well, the thing to ask yourself, voltage gated sodium channels, do they have anything to do with the resting membrane potential? I talked about sodium, potassium, ATPase pump, organic anions, sodium, potassium, all that stuff, but I never mentioned these. These play no role. Okay, so tetrodotoxin wouldn't change this one bit. Would it change the EPSP? Well, what causes the EPSP? Some is stimulation of sensory receptors. That wouldn't be affected. Neurotransmitter, so glutamate causes depolarization through the AMPA receptor. Well, that wouldn't be affected either. That's not the voltage gated sodium channel. So the EPSP would occur just fine. Now, the voltage gated sodium channels would open up. Okay, so they open up. But because they're clogged, no sodium comes in. So if no sodium comes in, what is our membrane, what's our action potential going to look like? Well, this depolarization, right, is because of sodium coming in. So sodium can't come in, we'll never get that. So the EPSP will fade away. We'll just return to rest. Okay, so tetrodotoxin would completely prevent the action potential. The effect that that would have on a person depends on the concentration, how much tetrodotoxin they're exposed to. What it would mean is no signals get through. So if I have sensory receptors telling me kind of what's in my mouth, and there's tetrodotoxin there, those sensory receptors won't be able to send signals to my brain, and I won't be able to perceive it. When we get an absence of sensation, we view that as numbness. That's how we perceive it. Right? So sensory wise, we'd be numb. Now, if I have high levels and it's throughout my body, my brain is sending signals to my muscles to help me breathe. Tetrodotoxin is going to prevent those signals from getting through, and I'm not going to be able to breathe. Tetrodotoxin is pretty nasty, obviously. All right. Any questions on that? We'll try one more. What if I have a toxin that holds the sodium channels open? And here, I mean the voltage gated. Okay, so there are some marine snails, for example, that have toxins that actually do this. There's a bird that has a toxin that does this. Okay, so if we have one of these toxins, we're at rest. Okay. Now I want you to think for a second, how is my trace going to change? So at rest, the voltage gated sodium channels play no role, so there'll be no effect. That EPSP, there'll be no effect. The channels open just fine. Sodium can rush in. Okay, so I get this massive depolarization. The voltage gated potassium channels that open. Now, normally these would close, but with that toxin, those channels stay open. Okay, so sodium will continue to flow in until it reaches equilibrium. Now, once it reaches equilibrium, even though potassium is flowing out, it's going to be counteracted by the influx of sodium. So essentially what's going to happen is we're going to get one depolarization that lasts for the rest of your life, which won't be long. Okay, so if we hold open the voltage gated sodium channels, we'll never get repolarization. Okay. All right. So that's kind of the basics of the membrane potential, of the action potential. Be able to predict how changes in ion concentration affects the membrane potential. Okay, this is at rest. Be able to predict how the action potential would be affected by various perturbations. So that's where we disturb the system. Okay, I gave you some examples. Hopefully those made sense. If in thinking about it, you have questions about this, send me an email and we can schedule a meeting. Is there anything, any questions you have or anything else you guys want me to go over? All right. This will be fairly heavily emphasized, so make sure you know it. Hopefully the review is helping you study, refreshing your memory a little bit. If you have any questions, don't hesitate to get back to me. Thanks for coming, and I will talk to you maybe tomorrow or the day after, I hope. Like I said, I'm recording them, so if you miss one, that's okay. I think it helps you more when you're actually here, though. Glad it was helpful. Thanks, and take care.